let's get going. Hopefully, you folks can see my screen.
Yes, we can.
Okay, thanks. So where we are going to start our journey today is discussing our own implementations of dataset and data loaders. Again, to place the whole journey in context so far, what we have done is started with some very basic linear networks, figured out what backpropagation means, distributing all of the gradients through the various parameters. So then we figured out how to code our own equivalent of PyTorch nn.modules. Once we coded and understood that, then we incorporated PyTorch nn.module, inherited from it. That gives us the ability to kind of control the parameters or access the parameters of the model very easily. And that began then our journey to optimize and or refactor the code for our training loop. And basically where we started the journey with respect to the training loop, accessing the training loop and so on, was this is what our original training loop looked like. Excuse me. For the epoch and then for values, because we needed to select a portion of the training data as batches, we kind of chunked, if you will, the entire training set into batches, sliced them, took out X's and Y's, which were our image and labels, used a model to predict it, found the...
Yeah, could you increase your font size, please? Oh. Maybe go into view and select presentation mode from there.
I think this, I increased it to 125. Can you, the notebook font size?
Oh, yes.
Can you see that now?
Yes. Yeah.
And then we kind of, this was our original training loop, or what he called the fit loop eventually. And where we focused our attention, so in the all of the refactoring that we've done so far, is in this portion of the code. We said, oh, what we can do is register the model. We need not check each of the weights. We can just access the model through the parameters. Then we have something called an optimizer, which enables us to do for each of the parameters just step, and we can take the gradient and multiply it by the learning rate and put it back in the gradients, and the optimizer can be zeroed. So all of this code was reduced significantly step by step, and we eventually have ended up with the training loop as it looks here, right? So we just said the simple thing we do after we get hold of X and Y is push it through the model, push the X through the model, the Y's are the labels, calculate the loss, which is our own predictions from the model compared to the labels, backward prop, test the optimizer, which means calculate the gradients for all of the parameters in the model, zero the gradients because we do not want to continue to accumulate the gradients, which PyTorch would do otherwise, and we repeat. Now, the remaining of this lecture, the remainder of this lecture will focus not on this top portion, but just simplifying. We could further simplify these 3 lines of code into a single line of code. And how we do that will be kind of the focus of the lecture, the first part. And for that, we use data sets, the concept of data sets and data loaders. So what's a data set? Well, it's kind of, if you can see, what we have to do here is take the entire training data chunk it, slice it, and then split it into X's and Y's. That's kind of somewhat of clunky code where we do XB is XP from the training data, YB is that. Instead, we could potentially combine the X's and the Y's into something we call a training data set or a data set class, and then extract X and Y from it. So the data set class, and again, notice that this is our own code, not PyTorch dataset code, but our own code. As always, he tries to kind of code the functionality using basic Python, the equivalent to PyTorch functionality, coded ourselves using basic Python, so we understand what the PyTorch equivalent functionality is supposed to be doing. We can kind of really grasp it through the code. And once we have done that, we can kind of switch to using the PyTorch version because it has much better performance code, much more optimized code, and so on and so forth. So this is our own dataset code. It says initialize the dataset with and just call the values X and Y. These are in our particular, in this case, the images and labels. And the dataset is essentially has, any dataset typically would have two items. One is the length of the dataset, that is how many items are in the dataset. In this case, we know, for example, it's 50,000 long, and that's typically the length of the input. In this case, the length of the images. By length, it's how many of them there are, not the latent value of the images, but how many images there are in this particular data set. In the training data set, there are 50,000. In the validation data set, there are 10,000. We know that already. And then we have a dunderget item, which in Python is how the Python translates this bracket access self.xi to, if we code the dunderget item then and provide it with an index, it will know to access the X value and the Y values at the index. So that's the simple definition of a data set. So now that we have a dataset class, we load X and Y train values into a dataset, call it the training dataset, and the X valid and Y valid into another dataset and call it the validation dataset. So we do that, and we have also confirmed by using the assertion statements that what we have coded here works, which is that length of the training dataset is the length of X train. That is, and of course, if we try instead of X train, Y train, this would still remain true. Then what we do is just to explore the dataset, we extract 5 elements from it. This is 0 to 5, so index 0 to 5. And then for each of them, we say that, or sorry, actually for all 5 of them, we say that the shape should be 5 of each image is a 28 by 28 chunk. Right? We already saw that. So flattened, it will be a vector of 784 length or 784 columns. So XB, which is a batch of 5 images, is of shape 5, and then each of these rows is 784 columns long. So that's what this says, and assert YB says it's just 5 because we just have the 5 labels corresponding to these 5 images. So we kind of confirm that. He's already defined what get model is. Get model basically says, it's coded a little bit further up here. Get model says, get me the model, which is just the model that we have coded, a sequential model of 2 linear layers with a ReLU in between. And then we also return not just the model, but the optimizer into which we pass the parameters of the model and a given learning rate. So we, again, get the model and the optimizer. And now you can see that we have kind of changed the code here from what it used to be. It used to be this guy, 2 lines of code. We've kind of reduced it now to a single line of code. Here, we just grab the X and Y from the training data set. And here we say, give me the minimum of I, where I is a batch size length chunk, or the minimum of N, which is the total length, and I plus DS. And obviously, this is done in order to grab, ongoing manner as we go through the loop. We'll be grabbing the batch size chunks, and then we come to the very end, we'll grab whatever is the minimum value there if something is left over of less than batch size. So we do that and make sure that our code still runs. And of course, we are still checking with respect to the training set itself, the prediction, and our model so far predicts fairly well at 0.96, and our loss continues to go down. Now, further simplification or refactoring of the data handling is possible, because we even now what we are doing is saying for I in the range of this between 0 and the length of the data set in chunks of batch size, and then we select X and Y. But we could potentially reduce these two lines of code and make them a single line of code, which would look like this. For X and Y in something we call a trained data loader. So if we can convert the training data set into some kind of a generator, which supplies us on a recurring basis chunks of X and Y, which is the image and the label, then that would simplify our training loop even further. Instead of these two lines, we can replace it with a single line, just like shown here. So let's do that. We define a data loader class, again, our own class, not the PyTorch data loader. And what we do here is to say, we provide the data loader with a data set. It could be a training data set, valid data set, any of our data sets that we have generated so far. And then we also provide batch size. And remember, if you recall, and if you don't, I'd encourage folks to go back and look at Python basics of how you code an iterator class in Python is by defining a dunderator method. And so here we define a dunderator method. And what that does, it makes the data loader an iterator. And what does the iterator do? Well, it executes this line of code when the next is called on the data loader class. So what does that do? For I in the range of between 0 and the length of the data set in chunks of self dot, I keep saying chunk, but it's actually the self.ds, which is the batch sized portions yield the self.dataset I and then I plus self.ds. So basically what this does is it generates an iterator which would give us the dataset portion starting from I and moving along in self.ds steps, right? So that's essentially what we want, because each time we want to start from 0, take steps of batch set steps and move along until we are done. So that's what the data loader does. So we create a trained data loader, pass it in the trained data set and the batch size, the valid data set loader and the same batch size. And having done these two, now because of the data loader being an iterator, we can now create when we call next on the valid data loader, then we get XB and YB, right? Because the data set has both X's and Y's combined as tuples. So XB and YB, and then we check to make sure that the XB we are getting is identical to what we got earlier. Again, we see that it is 50 because our batch size that we have supplied is 50, and each of them is 784 long. And when we look at YB, it will just be 50 values of integers, corresponding integers. Now we can look at an image of a single XB. Remember that an XB now is 50 values of 784 long each, flattened images. So if we want to access the first one, we say xb0 and we view it. But remember that the view has to be, it has to be reshaped in 28 by 28 size in order to get the image to plot clearly. So we plot that to be the, and it shows us to be the image for the integer 3, which we can see is the very first integer. So if you play with this, for example, if you say xb3, instead of 0, you'll say 0, 1, 2, 3, so you'll see the number 9 here. And obviously, yb0 says it's the integer label, which is the tensor 3. Okay, so now that we have done this, we again go back and implement that into our training loop. We get the model and the optimizer, and we define the fit function. And this is very concise, as short a code as we would like for our training loop. So what we do here is for every epoch, for every X and Y value in the training data loader, so each of these would be of batch size. We call the model on the axis, gather our predictions, push it to the loss function, propagate backward, take a step for our optimizer, which means we modify the gradients, zero the gradients because we don't want Python to accumulate the gradients, repeat the loop, and finish it. Keep doing this for as many XBs and YBs as there are in the data set. And once we're done, we go back and loop through yet another epoch for as many epochs as we would like to execute the training loop for. So that's essentially what we do. And we can see that just by calling fit and then calling the loss function instead of the report, we call the loss function of model in XBYB, and we code an accuracy function which just compares how accurate is the model, and we print those values. So the fit itself, because of this report function, gives us the reduction in the loss. You can see as we go through the 3 epochs, and it also tells us what our accuracy is at the end of this. Now, keep in mind that this is not such a great accomplishment because we are obviously training and reporting the accuracy on the training set itself. So our model is being tested, if you will, or we are trying to check how good it is on the same data in which we are training. But now that we've got the fit functionality in tight, let's say 7 lines of code or whatever, we can now begin to expand the functionality of our training loop and add in features. So all of our effort so far was in condensing or refactoring the code. So our training loop is as concise and as efficient as possible. And once we have done that, we can kind of go back to adding more bells and whistles to it. So the first thing we want to do is to say, what we are doing currently is we take the data which is in our data set, which is the training data set. And the training data set, the way it is, if you were to print out the data and look at it and so on, you'd find that the training data set is very kind of linear, meaning all the zeros typically come in the beginning, and maybe the ones, then the 2s and 3s and so on. That's what we would ideally like to do, is get our network to learn a bunch of things in random order. That is to say, our parameters, it's better for the network if it's exposed to 0s and 5s and 7s and 8s in some random order, rather than exposing the network to all 0s initially, then all 1s, then all 2s, and so on. In general, we'd like, therefore, a random sampling of the input data to be what our data set trains on. So how do we add that to the training loop that we have built here? What we import the Python random module, and we create a sampler class. So what does the sampler class do? Again, this is our own sampler class, Python coded. Our sampler class says, let me take the data set and a flag called shuffle, and I'm going to make the n self.n is basically the length of the data set, And again, I'm going to make the sampler an iterator. And what the
Yeah, I think we lost was.
Yeah.
yeah,
Okay.
my internet connection is dead, but I log into the phone
Okay.
for my voice, so I think I can still hear you folks, but my internet connection is dead. Let me try and reconnect. That's whether you folks can see it now. Then you know when you can see it.
Yeah, we see it.
Okay, so the sampler class is again an iterator, and basically what we do is create a list of indices, which is the length of our data set. And if our shuffle flag is true, we randomly shuffle it, and then we return iterator of the result. Remember that the result is nothing but a shuffled indices for the length of our data set. So all we have done here in a sampler is returned indices of length. And if we are using, for example, the train data set for MNIST, it's 50,000 long. So we would have shuffled a range of 50,000 and returned indices from 0 to 50K in random order. So that's all a sampler class does. And actually, we have seen this before, but basically he's just saying, look, in order to, we can use an iSlice Python code built-in functionality to create and use a chunk or build a chunk from our randomly shuffled set of indices. So we build a instance of sampler class, provided the training data set. So this SS would be an instance of the sampler class, and we build an iterator from it, and we just print next of the iterator in the range of 5. That means we build 0 to 4. Now, because shuffle is false, this is returning it in the order. So therefore, from 0 to 50K, this will still be in order. The results are still in order. So when you do the default sampler, which shuffle is false, you see that the indices we get are in order. And if you list them, it will convert it into a list. On the other hand, if we say shuffle is true, and we'll do the same thing, list of iSlice, but now the sampler is with shuffle is true, you can see that the indices are shuffled in random order, right? One of the things that Jeremy has done when he coded FastAI originally, I think in the second version of FastAI, is he coded something called FastScore. And these are essentially Python functionality, or I should say Python, improved Python or modified Python, essentially providing a lot of functionality that Jeremy feels is important and handy and nifty, because he can do a lot of things with the modified Python code that he has in FastScore. For those of you interested, I'll provide the link later in chat, but you can spend hours. In fact, I even had a class. If you're interested, you can look into that. That we went into the old FastAI version 2 library, and a bunch of the later portions of these were discussing the FastScore implementation. But FastScore has changed since then, so the best part of it is to go through this code functionality, if you will, when you have the time. But we'll kind of touch on the relevant portions as we go along in this course. So the reason he does that is, let's give an example of where he uses fastcore functionality. So one of the things Jemmy is big on is to have all of the code in front of you when you're working with the code, so that you can understand the functionality of the code, and it makes it easier to carry. As he says, the cognitive load is reduced if you can see all the code in front of you rather than having to scroll up and down on the screen, because then it interferes with your quickness of thinking, ease of thinking, and so on. So you can see how the fastcore code helps in this, because instead of saying, for example, typically what would happen here is he has this single line where he says use, because he has imported fastcore as fc.storeAttra. So this single line of code, if you go and check the fastcore basic functionality module, you'll see what it does is that it stores the attributes that are defined in the init function. So this single line of code is equivalent to saying things like, which is typical, self.sampler equals sampler, self.ps equals ps, self.droplast, you get the picture. So instead of having these three lines of code, all of which says self.sampler is sampler, self.ds is ds, blah, 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 which increases the cell size, and you just say that, and it essentially does the same thing. It initializes the values in the class and sets them to the values that are there in it. Okay. Similarly, if you look into the fastcore chunked code, and I can show you this one. Let's just check chunk. So here is chunk, and chunk just says you pass in an iterator, you pass in an optional chunk size, and you tell it whether to drop the last chunk or not, because the last chunk potentially could be smaller than the batch size. And we'll talk about why that matters in a little bit. And then you can optionally give it the number of chunks. And then what's really good about the fastcore is, it tests the coding of the function. You can look at the source code here and the tests that are run, and you provide a variety of inputs, and you can run all these tests yourself. So the beauty of all of this is to say that there is no magic. You can code pretty much anything and understand most of what the code does, thereby giving you the flexibility to modify anything that you need. So this, and it says chunk returns batches of iterator IT of size chunk size, or return the number of chunks total. So you can tell it one of these two things to provide. So what we do here is we say yield from fc.chunk, and obviously this is the iterator. The size we want is ds, and whatever we drop last is for us, which is typically false, which means don't drop the last chunk. We provide that as an input as well. And the reason for dropping or not dropping the last chunk is the following. Typically in GPUs, everything we try to process, and the GPUs are optimized for batch processing, the batches ideally should be of the same size. Otherwise, the performance gets impacted. And so it is okay when we have 50,000, when we have 1 million samples, for example, in our tests, in our training data and so on, to optionally not grab the last chunk, which if we are dividing 50,000 by 64, for example, if our batch size is 64, our 50,000 divided by 64 would not be, would result in the last chunk being smaller than our batch size. So if we set up the GPU to process batch size chunks constantly, and then the last one is a little bit smaller, it kind of interferes with the performance. It really doesn't matter if we ignore 64 examples out of millions of examples. So typically you'll see drop last being set to true if we have very large training sets, because the last chunk may not be equal to our batch size. But it doesn't, it's just a feature that gets set or not. Now we choose batches.
What does yield from signify here?
It just says yield. And again, you can look at what is the yield from functionality in Python. It was introduced, I forget, in 3 point some version. But basically, it says from this iterator, yield the chunks of batch size. And instead of just writing, this could be written as first return that and then yield the chunk, but instead you can simply write it in a single line of code as yield from this, and what you're yielding is chunks, is whatever this function returns. This function returns batch-sized chunks, as we saw in the fast4 example. So for example,
it's basically a for loop, for I in this yield.
Yeah.
Right. Yeah.
But the improvement is you can directly yield it from this guy in a single line of code. That's what yield from this function says. So essentially, coding batch sampler with the SS instance and 4 as our batch size, and obviously drop last is false, gives us the batches. And then when we slice the batches, let's say, remember that this would provide us all of the batches, and we slice it to just provide us 5 batches. So this means each batch is of size 4 because our batch size is 4. And when we list the slice of batches, the batches is all of the batches from our data set. And we slice it to provide just 5 as examples, and we see each of the mini batches are 4 samples. Okay. Now, here we run into a slightly different problem. Remember what we had done in the process of setting up our loop was we had combined the X's and the Y's in our data set, right? We had said, let's take an X and a Y and put them together, or the X's and the Y's, and that will form our data set. But when we want to process the X and Y's in the training loop, we want sets of X's and Y's, not tuples of X, Y's. Okay, I hope that's clear. That is, each of these indices in our data set points to a tuple of X, Y. Okay, an image and a label, an image and a label. So each one of these is a tuple of 2 values, image value and a label value. But what we want eventually when we process the these in our training loop, as you can see here, if we want the X's together and the Y's together from our training data loader, even though the training data set and the training data loader has them as tuples of X, Y's. So we want to extract from the batch has tuples of X, Y's. We want to extract all the X's and create a group or a batch of X's and a batch of Y's, because that's what we want in our training loop. So how do we go from what we have in our training set and training data set and the training data loader, which are tuples of X's and Y's, to sets of or tuples of, or actually just stack of tensors of X's and tensors of Y's, which is what we want in our training loop. So that change or that modification is what is done by the collate function. So let's understand what the collate function does. And again, this is our own collate function. PyTorch has its version which we'll use, but again, let's code it ourselves so we understand what it does. If we supply a batch And remember, again, a batch is a batch of XY values, right? So this batch has, if it has 4 values, it has 4 tuples of XY values. So what we do with it is say star B, and this is basically referred to as a splat operator. So what this star B does is, it removes, if you will, if you just did star B and put X and Y, it will split the XY tuple and provide the X and Y separately. And then when we zip it, then what happens is the X's get zipped together and the Y's get zipped together, as it were. So you would get a group of X and a group of Y. So that's why these are X's and Y's. So this is a very common transpose thing that you will see done very commonly in Python, which is the zip star concept. So zip star of a value will essentially, let's say the value B is a batch of tuples, then a batch of tuples of XYs, then the tuples get split into X and Y's, and then the zip zips the X's and the Y's. So what you get out is a set of X's and a set of Y's. And then you just stack the X's into torch values and the Y's into torch values. So that's what this says. And as you can see, I add a lot of comment as I go through these notebooks so that I kind of make sure I understand what the functionality is, even if I were to return later and try to grasp what it's doing. But so this is collate function is essentially a function turning a collection of batches into what are fit or what a model can use. So the X tensors and Y tensors of batch size length. Any questions?
Yeah, just to
Okay, once you've done
confirm.
that.
Sorry, I have a
Yes,
question. So the zip actually zips the X, S and Y, S, or unzips it? Like, does it form into one tuple? Just to make sure I understand.
No, it doesn't. And what I haven't done here, you could, I would suggest playing with small amounts of batches that you can create, and with each of this, in words, what I can tell you is star B splats. So if you had just these indices, let's say, for example, and provided that if you say B were just a series of indices, which were these 4, and you did a star B, then what you would get out into before the zip, if you just did, actually, if you said B were, let's try that, because that could be, B is a, B, then X, Y, and stuff. And let's see.
You forward to
Oh,
our
it needs
zip.
to be. Yeah, but I wasn't trying to, but I guess you'll need to call it within a function, which is when splat works. Okay. Then, so, oh, it, Typically, we provide, or let's even just try this. Okay, this. Tuples, which is each of these is essentially and zip star t and print x d by t. You see, what it did was it split it into zip star. So xt became the axis as a tuple, and yt became the y values.
Okay, yeah, I get it now. So basically, it's zipping the x's together and the y's together.
Correct.
Like making it into, yeah.
That's what I was trying to say.
Oh, okay.
So that's why you see it as a transpose function, right? Because what is, laid out as x, y's, it combines the x's and creates a tuple, and it combines the y's and creates the tuples. And in the data set, we had it laid out as x-y combinations, which is not what we want when we want to process. We want x's together and then y's together. And that's what this functionality does. And I really encourage folks to play around like what I did here in order to really understand what the functionality is and how it works. So you can see what it does here with this simple example, right? It changed the example from if this was x and y, it combines the x's into a tuple and it combined the y's into a tuple, which is what I was trying to say, that star bt, basically the starring takes the 2 and the 3 and sticks it in each of these, but then the zip zips the x values together as a tuple and the y values together as a tuple. I hope that's clear. Okay, so now we understood what the collate function is used for. And basically here, what we have done now is instead of just saying yield from fc chunked iter, we say yield from the collate function of the data set I for I in B for B in self.batches. So again, as Jeremy does in the code, and in the interest of time, I'm not doing it here, but I would really encourage you to split up as we did in this example, split this up into different pieces of code and see what this single line of code is doing. Basically, what it's doing is taking batches, so taking each of these 4 guys, which is a batch, and so that's a B in self.batch is these 4 indices. Remember, each of the indices has a tuple of 2 values, x and y. So for each index in B, so for each of these I in B, it takes the self.dsi, which means it takes the x and the y from the data set corresponding to this index. So it takes the image and takes the label corresponding to I, which is this index 27552 in the first case, from our first batch, because that's the B, and it collates it. So that means it takes the X and sticks it as the tuple, and it takes the Y. So in the next thing, when we do the I move to this guy, it takes the X and takes the Y and sticks them together. Same thing for this one, same thing for this one. So when it's done, when the yield is done, you should expect 4 X values and 4 Y values if we stuck with using batch size of 4. But if we use 50, then it would have yielded 50 tuples of 50 X values and 50 Y values, similar to this providing 2 X values and 2 Y values. Remember that we would have provided 50 as the batch size, so we would get 50 X values and 50 Y values. Okay? So that's what this single line of code does. It creates a corresponding and appropriate X and Y tuples that we need in our training loop. Okay, so that's it. And now we can make things simpler. We can create what is called a train sampler, which is basically a batch sampler of the sampler class. So essentially, a sampler class, remember, is something we just said whether or not to shuffle. So if in the training case, we shuffle. In the validation case, we just wanted to predict whatever the value is. So we don't necessarily care about shuffling the validation set. In fact, we shouldn't. So the shuffle flag is set to false. In case of training, we want the data set shuffle, so we set it to true. We built a sampler class instance, provide it to a batch sampler with a size of batch size, and we get a training sampler. So training sampler is nothing but a batch sampler. That means it's a sampler of size of batch size, and with the flag shuffle set to true or false. And correspondingly, we can set the drop last appropriately as well. So once we've done that, remember, all this is in the context of enhancing our capabilities of the training loop. When we say a training loader is a data loader, and we provide it a training data set, and our batches are a training sample data set, class, train sample. And train sample is an instance of a batch sampler with the shuffle set to true of size batch size. Okay? By doing this, what we've done is we have enabled the train data loader to provide us chunks, which are collated chunks of X's and Y's. Why? Because we are really returning self.collate function, and then of size batch size. Right? So we have kind of enhanced the capability of our training and validation data loader. So now we can go back to using next iter of valid DL, plot the value, see that it returns, something that we haven't. Basically, these steps are just to ensure that we haven't made any mistakes in our coding. Everything still works as we think it should. For example, XB should still be 50 by 784. YB should still be of integer length 50. We get the model and we train fit. Essentially, this just says, hey, we have made this modifications, added the samplers, added batch sampler, added kind of shuffling capability, and we have still retained the functionality of fit. Now, I think you'll notice. Yes.
One question. So if you look at where it does the shuffle true for the training set and shuffle false for the valid set, right? So I know the logic for this. I mean, people, but I've never really thought through it. And maybe, but now that I think of it, I don't really see it. So this question, right? So that the logic here is that, you should not shuffle your validation set, because every time you're going through it in a potentially different order, and that can affect your validation results. I don't really see how. I mean, is it because we are doing averaging by batches?
Yes. It isn't. That's a good question, by the way, Sujit. I think my rationality is as follows: that typically the validation set is, unless there is a negative connotation to the training set being in sequence, because that in potential negative consequence, I should say, because that implies that you're training on.
Right, yeah.
Right. It doesn't. You don't want to tell it that zeros come first, then comes one, then comes two. It doesn't. Is not typically the case, right? So we can clearly understand why this should be the case. Now, I agree with you that. Sorry, go ahead.
No. I think I know what you're getting at. Basically, because it doesn't matter. Right, whether for validation the order does not matter. Okay, I got it. Right.
Exactly, it shouldn't matter.
Right.
So it's not so much that but there is another reason potentially, which is if you shuffle, I take that back, because as long as you ensure that your sampling is not sampling with replacement, you're still okay to shuffle. But there's no point in shuffling because it doesn't matter.
Right.
Yeah, that's the way I understand it.
Okay, got it. All right. Thank you. Yeah.
Right. But here you do want to make sure that it's shuffled.
Right.
So in all sense, I think it's more important that your training shuffle be true than whether your shuffle or the validation is required to be false. But it's safer if it's, or it's preferred if it's false. The way I remember it or recall it. Okay, so what we've done so far is we've coded all this data set, data loaders. But see, when we load the data set, right, when we do this self.dataset I for I in the batch, that is for each of these indices, we could be doing a lot of things typically in training. What do I mean by we could be doing a lot of things? What I mean is we could, for example, be taking an image, say a JPEG image, and rotating it, stretching it, flipping it. We could be doing what are called augmentation, which is in order for the training to be robust and for our model to learn things which don't depend, for example, on the sequence or on the way the image looks, if it isn't shuffled or rotated or stretched. And we want to make the training and our model robust to those changes. So we may end up, or often we do end up, doing a lot of work when we access each of these X values, in this case, images. Now, what we would ideally like is for each of the image, for example, would be stretched, rotated, flipped, and so on. Now, typically these days, our computers come with a lot of cores, right? There could be 4 cores, there could be 60 cores, there could be like 12 cores. Forget about, I'm not even talking about graphic processing unit, I'm just talking about CPUs. Even CPUs come with a lot of number of cores. So ideally, what we would like the data loader to do is to take each image. Say if we have 4 images, because we have I will be 4 for each of our batch in this case, or 50, then for the 4 of 50, if we have 4 cores, I'll stick with 4 as a simple example. If we have 4 cores, we would like each image to be given to a separate core to process, because that will speed up our processing compared to if we just were to run the processing of each of the images in sequence on the same core. Now, that kind of processing is typically called multiprocessing. And handling multiprocessing in any kind of Python code, and typically with tensors and so on, is fairly complicated because you need to ensure a lot of things happen in the proper sequence and get recombined in the proper order. That requires significant attention to detail in the code. But, and therefore, the PyTorch data loader, which is actually a fully multiprocessing data loader which supports tensors, actually has a lot of code in it, which recodes Python's multiprocessing capabilities. Okay, but what he is doing in the remaining of this particular lecture is illustrating again what one way by which multiprocessing can be done in our own data loader, and then he switches off to the PyTorch data loader. And the reason for using the PyTorch data loader is that it has all of this complexity of handling multiprocessing, distributing the multiprocessing code to the various CPUs or GPUs, and then recombining and creating the correct sequence of our data is a detail that's fairly involved. But he's just illustrating how using our simple Python code, we could potentially do it. Okay. He uses the MP module, which is torch.multiprocessing, instead of using Python multiprocessing. And again, he says in the lecture, the reason he does that is the Python multiprocessing doesn't work for a variety of reasons with the torch tensors very well. So he kind of borrows the torch multiprocessing capability from PyTorch and calls it MP. And then basically he just says from Fastcore basics import store address. Here, what he's just illustrating is, remember that using these square brackets or a list providing to train.ds is basically saying, hey, train.ds, go get these set of items, or go get the use the dunder get item method to access the values from each of these locations in the training data set. So this says training data set at location 3, at 6, 8, and 1 is what these X values are. And remember that I keep repeating that at each index of the data set is a tuple, an X and a Y. So the X is this, that's the image. The Y is that. So we get at 3, 6, 8, and 1, these 784 values, which are the images, and then the corresponding indices, or the corresponding labels, I should say. So this guy, train.ds 3681, is equivalent to, so train 3681 gives us that. It's exactly equal to train.ds.dunderGetItem at 3681. Now, what we can do then is, this is, of course, we saw this as a flat set of indices, but let's say we split this into 2 batches, okay? A batch of 2 values. So a batch of values of 3 and 6 index, 3 and 6 indices, and 8 and 1 indices. So these are 2 batches of 2 values each, for example. Then what we do, and again, this is just an illustration of what he says is the example of map function. So map basically says execute this function on each of these values. So mapping something, so map of f on an iterable is typically the nature of what a map function looks like, which means take the function that you specify map, in this case, the get item function, and execute it on each of these. So when we do that, for the first tuple, you obviously get the X and Y value from 3 and 6. So that's why we get the X values, 3 and 6. That is not 3 and 6 actually, but the indices 3 and 6, whatever the image values are, and then the corresponding label values. So you can see that the label values are 1 and 1. So you get 1 and 1 here, and the label values for the next tuple are 1 and 0 for 8 and 1 index, 8 and 1 index. So the tuple values are 1 and 0. So we just step down in map, right? So why does this is just a simple example of the way map works. So now what we can do is we can use this map functionality and the multiprocessing modules coded in from Torch multiprocessing as MP, and then you can pool it and provide the number of workers as input. Think of n workers as the number of, say, cores that you have in your computer. So you could potentially pool the number of computers, and with mp.pool as an execution function, it's just a context, you yield from and you map the EX onto the, you run the map function on the get item and an iteration of self.bat. So what this guy does is it introduces multiprocessing of the get item, so that in this simple example, it would execute getting the image and the label from the first tuple on the first n worker. If it's 2, let's say for simplicity, let's say it's 2, then it runs these 2 values on the first CPU and these 2 values on the next, which begins to support multiprocessing. Now, this is just a very simple example. The actual PyTorch code can distribute it over available number of cores and how it does it when the cores don't match, and there's a lot of detail behind it. But the point of it is to show that you can potentially, with a simple extension to our own data loader code, we could support the case of multiple CPUs and support multiprocessing. So train data loader, provided the data set, provided the sample, and then you give it the number of workers is 2. Now this is a new value that we are providing. So by doing this, we have actually distributed the get item over, or when we get the tuples from our data set, we are actually dividing the work up among the multiple cores, thereby increasing the speed at which we do the work. And that's where this guy still now, by supporting X and Y extraction, the difference is that each of them is getting distributed to 2 cores. So our work would get done faster. Again, the stuff here where he starts with multiprocessing data loader is just an example. This is, the actual Python data loader does a lot more complex stuff to ensure and guarantee the best handling of multiprocessing. And multiprocessing working with tensors is a fairly complicated problem, which is the reason that we don't do all of this ourselves. And having explained kind of the basics of dataset and data loaders and how potentially a simple example of a multiprocessing data loader could work, he now switches to using the PyTorch data loader. Okay. As always, remember that the thing that he always does is code the equivalent functionality yourself using basic Python. And once we have that working, we are free to switch to the framework's corresponding functionality. Any question? Okay, so now we are kind of into using PyTorch data loaders. So we kind of from torch.util state data, import the data loader sequence. And unlike in case of the way that he has coded it, where he coded a single sampler and created a batch sampler and just had a flag, here PyTorch does this, which is it has a sampler which is sequential and a sampler which is random. As he says, he doesn't know why it's done this way, but anyway, it's not a big deal. It's just, conceptually we can understand what a sequential sampler is and what a random sampler is. Sequential will return the indices in sequence, random will return it in random order, and the rest of it is all the same. And batch sampler will mean that it will return, it's a sampler and it can be of sequential or random, and it will return as a batch of indices, either in sequential or in random order. So we then obviously define a train sampler, which is a batch sampler of a random sampler of a trained data set. Why? Because remember that we wanted the training data set to be sampled randomly. And here in both cases, we have set drop last equals false. That means we choose to drop the last chunk, which could be smaller than that of a batch size, for example. We create the training and validation samplers, and we patch them into the data loader of PyTorch, and we call the default collate function. In this case, we call R1 collate function, and we form the training and the validation data loader. Again, remember that the collate function is needed in order to compare it to the zip star B functionality that we saw. So it converts the tuples of X, Y's into stacks of X tensors and Y tensors. Right? Then again, go back and check everything works as we used to before, and it does. Now, these last few lines is just an indication that we can actually do away with a lot of this kind of repetitive code or things which are assumed to be the case in a particular situation. So basically, PyTorch can auto-generate the batch sampler for us. So what it means is instead of creating these training and validation samplers and stuff, you could just say sampler is this, and you can say collate function is collate. But again, so it simplifies that somewhat by providing that the batch size and the samplers. It can also generate sequential and random samplers. So you just give it BS, and instead of telling it all this, you can just provide shuffle is true, and it automatically creates batch samplers of size BS, and make sure that as long as shuffle is true, it will automatically pick the random sampler. And if shuffle is false, it will pick up the sequential sampler. And in this case, both cases, you say you can additionally provide the number of workers, because because remember, this is the PyTorch data loader we are using. It means it's capable of supporting multiprocessing. Okay, again, we just run the code, ensures that we have done everything as what we do. This has not changed. Functionality is exactly as we wished it to be. There's one thing he points out that I had a question for myself. I believe I kind of understand it, but I'll, if somebody else has additional comments on it, feel free to jump in. He also points out that, look, our data set, which has the capability to kind of get or acquire multiple elements, like, oops, that's not 4, 6, and 7. Okay, so because it has the ability to kind of grab multitude of these indices at the same time, we can kind of skip the backsampler and collate functions. Those are, not necessary to be provided. You can go ahead and play with it and understand it didn't seem really material to our discussion currently, but that's the reason I added a note to myself here. But bottom line, what it seems to say is because of our ability to, in our dataset coding, to grab multiple items at once, we can simplify what we provide to the training and the valid data loaders. Of course, these data loaders are still PyTorch data loaders. It's not material to what we are discussing here, which is the reason that it wasn't key to our understanding of what we are covering in this part. It's more related, I think, to how we handle the Hugging Face data set, which we'll move to next. Now, once you've done the enhancing of the data set and data loading parts, we can also split up the training into two pieces, the training part, and then remember, until now, we were evaluating on the training set, which, as most people, if you've gone through anything in data science and stuff, you know that that's not a very good practice, or even not the thing to do. You don't want the model to be checked on what it has been trained on, because quite often it kind of has, or it has always seen all of that data. You want to check it on data that it has not seen. So it means that you create something which is called a validation data set, which is completely different from what you've trained the model on. And to do that, we kind of create or now begin to expand the fit function again and have a portion of it with trains and a portion of it which the training portion runs on the training data set and the evaluation portion runs on the validation data set. How we provide the data to the data set and how we train it is exactly the same. There are a few differences in how we handle data in the training and the evaluation set that I'll just touch on. The first thing we do, which is different from what we have done before, is set the model in the training mode when we are in the training phase, so to speak, or when we are doing the training. And this is the model.train basically is a flag to the model in our PyTorch code, which says set the model in the training mode. And there are reasons as we go through further in the course, we'll understand why this flag setting is important. For example, there are things like dropout and other things, or even batch norm, which is a norming function that we execute. And the way that that function behaves is different in the training than it is in the validation. So because certain functions behave differently in training than they do in validation, it's important to set the model in the training mode, as it were. And that's why the model.train call happens before the model is trained. Otherwise, this code is exactly the same as before. Exactly for the same reasons that I said, that the behavior of certain functions is different in the training phase than in the evaluation phase. You want to make sure that when you are in evaluation phase, you tell the model that you are in evaluation phase. So that's why model.eval call. And then this portion when we train is when we compute the gradients and we propagate it back. Once the model has been trained and its gradients have been computed, we do not want, when we are checking the model, that is when we're just using the model to do the predictions, we do not want the gradients to be altered any longer. We fix or freeze the model parameters. And that's what this with torch.nograd line does. It fixes the model parameters. It says take no more gradients of the model when you are in the evaluation phase. So that's the context in which then we calculate the losses. This is identical to what we do here, except we provide the validation data set, and then we push the prediction to the model, calculate the length of the batch, add the count, average the losses, calculate the average accuracy, and print the average accuracy, which is total accuracy by count, total loss by count, tell it the epoch, and then return the values. So this is our modified enhanced fit loop. Okay. Now he threw in one more functionality here, kind of not related to it, but let me take a minute to explain what it does. It just says get data loaders function. So basically what a get DLS function does is you provide the training data set and the validation data set and the batch size and a number of keyword arguments. The get DLS, just like get model, returns a data loader of the training data set with a batch size, shuffle is 2 and with the keyword words, and a data loader of the validation data size. The reason it does this is because typically when we are training, and not typically, always when we are training, we are calculating the loss and we are backward propagating. That means that the memory that it uses is much larger than what we do in validation, where we don't calculate the gradients and stuff. So in the typical case, we could support, that is our memory, if we want to use our memory efficiently, we can increase the batch size of validation data sets or data loaders to be 2x that of our training set. Because why typically the difference here in the doubling of the validation data loader size, batch size, is because we use a lot more memory to compute the gradients. That does not happen in the validation loop or in the model.eval portion. That's why we increase the batch size significantly. That's the get data loaders functionality. And then now we can just simply say train DL, valid DL is get data loaders, model opt is get model, and then loss and accuracy is fit. So you can see how the entire process has been simplified through get model, through get the data loaders, and then this fit function that's right here. And with these 3 lines of code, you can pretty much now train a simple 2-layer neural network and get it outputting most of the interesting data that we seek. Right? The one thing which Jeremy has historically done is use the notebooks to generate a lot of functionality that is used in code that he uses as part of the libraries and various, explanatory capabilities that he provides. So, for example, FastAI or FastCore, all of these kinds of frameworks, tools are developed using notebooks. Why? Because it's, as you can see here, there's a lot of documentation. There's a lot of explanatory things that can go along with this code, right? So the environment that he uses for it is called NVDev, short form for notebook development. So wherever you see these commands like this, bang, pound, bang, export, it's not bang, but pound, whatever, I forget what he calls this export. This is actually saying to the notebook development environment that expose this cell and store it away for future use. So in subsequent notebooks, we can import the relevant module. So for example, up here, I don't know whether we do this in this case. By the way, that's the reason and this is not default included in the notebook. So if you're trying to use the notebook, make sure that your notebooks are located in where I think there is a particular file that's needed. So you need to run it in that location where the file is present, and then you need to pip install -e dot. That then allows you to, for example, import certain things. I think it's not essential for this, but when we go to the next notebook, I'll illustrate a situation where he imports a module from what he calls Mini AI. And the Mini AI module is important if you want to use it to have that pip install -e, and also to do the exports of these guys. Okay, this is for me to shut down this. So that's it. We'll now move to the second part of using the dataset and data loaders, and that is to work with Hugging Face datasets. Because so far we have been kind of using just the MNIST dataset, but Hugging Face Hub, if you're not exposed to it, I'd encourage you to log in, create an account on Hugging Face, and play around with the datasets that are available there. It's a good playground of vast variety of datasets that are available. While I'm setting this and running, any questions so far? Any comments on speed? Should we go faster, slower, appropriate speed?
No, I think this speed is pretty good. Maybe as we get deeper into like doing callbacks, we can discuss the actual how that works, because that's what I've been having issue. But yeah, I think the speed is good. Can I ask you, do you like this export is being saved in a .py file, right? Somewhere, and then it's being re-imported in the next notebook?
Right. So for example, as told you or promised you that I'll show where we will need the reason why we are doing the pip install, blah, 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 is because of beginning from this notebook, you see this guy from Mini AI training import staff. So you're actually importing some of the stuff that you're exported from prior work. So those pieces of code that you saw in this notebook, like DLS, like get DLS function, the fit function, there may be others way up here. This guy, those things, when he says pound bang export, he's exporting it to Mini AI, and then in the future he'll import it. And the reason is that means that these lines of code or these functionality is available to him, much like any other module that we import. Just like he uses fast code imports, he's also using code from Mini AI training. And actually, if you have installed this, and I have it installed on Google Drive and stuff, you can actually go into Mini AI and look at the training notebook. These are nothing but modules. That means there'll be a training.py, and you go into training.py and you can see the stuff that is actually using from there. Here, the star, typically people say don't use this syntax, but in his case, in a particular environment that he sets up and stuff, this is perfectly fine, because every module that he has automatically in NBDev has the dunder all to be defined to be certain functionality. So he limits it that way, and because all this is done with scripts, it's all automated to the point that he doesn't pollute the code, which is the concern as to why people most often say don't do import star typically. But because his thing is all set up through scripts, that's not a problem. Oh, you had a question?
Well, unless it's somebody else, I was kind of making the point that, do we really need an additional, pip install for this? I mean, maybe, if nbdev was like a standalone thing, it would, pluck out parts of your cells and write it out into a file, right? And the file is sitting in the same directory as where the rest of your code is. You should be able to just from that file name import star, and all your things, all your function definitions and your import should work.
Yeah, I struggle with this, Sujit. Part of the reason, again, I just installed all of this or copied all of this onto my Google Drive from Git install,
Right.
and it sets up a particular structure. The root cause of why the pip install -e dot is needed, as I understand it, is because Mini AI, unfortunately, is not a fully formed library, so he hasn't created a library from it.
Right. So you're pip installing from the Git itself.
Yes, and that's why, because it's kind of locally done and stuff, and he hasn't created a pip install Mini AI kind of package from it. That's why we need to go through these hoops for right now. That's the way I understand, because in fact, originally I was running from host 22 P2 notebooks, which is where my notebooks were. That's not where, I forget now the name of the file that is needed.
Oh, I see.
That file is actually present in the host 22 P2 directory. So I had to copy over the notebooks here and run it from here in, because the pip install works in this directory. So it's a complicated function of the, Git install, Google Drive, how it installs or how he has it set up, and those kinds of things. So it took me, in fact, a couple of days to figure this stuff out and get it all working now. Okay, so and then, the pip install datasets is actually installing a lot of the Hugging Face datasets. And we'll kind of begin to see why a huge variety of datasets are available in the Hugging Face Hub and Hugging Face datasets. What's funny, and I hadn't realized it until I went through this notebook, is Hugging Face datasets have their own way of dealing with things, which apparently I didn't grasp it because a lot of it is hidden behind PyTorch functionality, but it's good to know. Is Hugging Face deals with datasets not inherently as tuples, but as dicks. And that causes some level of, you don't need to, because if you eventually, once you abstract PyTorch handling of the datasets, then it becomes kind of moot, I think. But it's good to know the details, because I've encountered some problems with Hugging Face datasets in the past, and now I understand why better. So we'll see as we move through what I'm rambling about currently. Hugging Face datasets, just keep in mind, are things which provide, remember, when we looked at MNIST, the X and Y was available to us from the dataset and data loaders as tuples. And they were stored in the dataset and data loaders as tuples, even as in the PyTorch MNIST dataset. In the case of Hugging Face dataset, you'll begin to see that they are stored as dicks, not as tuples. That leads to a little bit of change that we have to make in some of our code. You import datasets. This datasets, again, it's a small dataset, and it's a Hugging Face dataset. We install that, we import the fast correlated imports, do the setting up, and we do the following. We give it the name of the dataset that we want to use. Currently, we are using what is called a fashion MNIST dataset. So it's very similar to the MNIST integer dataset, except it's a set of 10 images of different clothes or different You'll see an image in a minute. So the name is fashion MNIST. The dataset builder is something you provide the name to, and then the dataset builder has an attribute called info, and that has an attribute called description. It can give you the description of what a dataset is. Training set, again, of 60,000 example, validation set or a test set of 10,000. Each example is 28 to 28. This should all be very familiar. 10 classes, very familiar. And it's like a direct drop-in replacement for MNIST. And we'll be using this data set all the way through autoencoders and so on and so forth. A little more complicated data set than basic MNIST data structure. Now, this is where you begin to see what is meant by Hugging Face uses dicts instead of tuples, right? And tuples are what are used in PyTorch, tuples are what are used in FastAI for storing X and Y values. So you do this, DS Builder info features, then you say, then it tells us that the features of this particular data set, fashion MNIST data set, is an image of type image and label of type class label, and its names are these 10 values. So this is, corresponding to kind of the 10 integers 0 to 9. So here you have a t-shirt, a trouser, a pullover, various forms of dresses and stuff. And then we can find information on the features from the image and the label, information on the splits from the info splits. And now what we create, this DS Builder is just the saying load information about the data set. It's not actually building the data set. What builds the data set is the load data set. By build, I mean load. The word. So the data, and the reason he calls it DSD is to remind us that this data set is actually composed of dictionaries, not of tuples. So DSD, load data set, and you give it the name. The name is the fashion MNIST, and you get DSD. So it loads the data set, and it will take a while to load. But while it does that, the thing then to understand is that DSD has a train and a test, right? And it's a dictionary. So DSD train is the training portion of the data set, and DSD test is the test portion of the data set. You can see that DSD is a data set dictionary, which then has a train key, which is again a data set that has features, which has image and label, and then it gives us the number of rows. Okay, so train data set, train and test is DSD, which is the data set dictionary. Train will be equivalent to what we saw in the training MNIST train data set. Okay, so DSD train is DSD train will then have features and rows. And train 0 will have, and again, remember train 0 is again not a tuple, but a dict. And the dict has an image, which is a PIL image, 28 by 28, similar to what we had for the MNIST, and a label, which says 9. Now, obviously, we have to convert the label 9 into the names that we saw for the labels, and that is what will give us the actual name. Is it a t-shirt? Is it, I don't know, pullover, ankle boot, whatever. Okay. So there's a little bit of further processing to set up what we need in exactly the way we want it to be. So here I was just playing with it to see, okay, what is the type of train? And you can see that train is actually a data set. And then DSD is a data set dict. Now he says, well, I'm not going to bother typing image and label each time. It's too much typing for me. I just want X and Y. X is image and Y is label. You can therefore say X, you could just do it in a simpler way as well. X is the string image and Y is the string label. But the more appropriate way to do it is to say DS Builder info features. So that's what this done. So DS Builder info features is image and label. So when you say DS Builder info features, there will be image and labels on the right. And when we give it two inputs, X and Y, then X will become image and Y will become features. So that's what that does. So, I mean, he's just, again, the first line isn't actually needed now that we did this, but X and Y is image and label. Image is train 0x. So we want train 0. So that's the 0th element of train, which is the first tick, and of that we take the image value. And that is an ankle boot. That's the ankle boot that you saw here. Now we can do the same thing as grabbing 5 of them at a time and print that, and these are the indices into our label names, right? Now, typically what we do is train.features y will give us the feature y. So this would say, what are these features? And so feature y, when we print it for the 5 values or all of the labels, will be these 10 values. Now, in order to begin to convert these indices into actual names, typically we have functions on these called into string or string to int and so on. And by using the into string function, so basically it says, take the integer and convert it into this string. So you can see when you do vty, and the first one is 9. So 9th value here, assuming this is 0, or let's pick an easier one, the next two are 0 and 0. So the 0th value is t-shirt top. So that's why you see t-shirt top here. The 9th value is the last value here. That's why you see the ankle boot, right? So we see 9, 0, 0, and 3. So 0, 1, 2, 3. So that's why this is dress. So that's that. And the training of label of 5 is essentially the same as this. Label and Y. Okay, but here's where it begins to get interesting of how to handle Hugging Face data sets and so on. The thing we were doing, if you recall from our original collate function, is the zip star B function, right? So that's what we did with and then we added a dot stack to it. Now what we need to do is, because it provides us, the Hugging Face data set provides us with dictionaries and not with tuples, we need to handle the dictionaries and return a dictionary as well, right? So in this case, we need to change the collate function to return a dictionary of stacked images and labels. That is for X and Y of the Hugging Face data set, right? So what we do here is we create a dictionary, and then we do this TF is actually what he imports as TF. It's dot vision transforms. Okay, so you're basically using vision transform functional as TF. It's TensorFlow. So you use the functionality from dot visions, convert it to tensor of O of X for O in batch. So for every O in the batch, which is basically an index in the batch, you do O of X, convert it to tensor, stack it. For O of Y, for O in B, convert it to tensor. And because this is just a flat tensor, we don't need to stack the guy. So that's what we do. We convert the collate function to return a dictionary as well. Okay. Then the data loader, exactly the same. We just pass in our new collate function and we say batch size of 16. And then that's what our data loader is. Our batch now can be next of iter of DL. Then bx.shape will be, because remember that we have images of 28 by 28. So the shape of this is 16, 1, 28 by 28, and then 16 values which are all integers pointing to the labels. We could potentially have manual collate function functionality like this, but what Hugging Face provides is the ability to run a transform on a data set or a batch of data inputs, and we can use a formulation like this. A transform data set is the training data set with transform, and you provided the transforms that you want to run on it. Okay, so this is what we are aiming to do, and in order or utilize, Hugging Face provides this capability, PyTorch supports it. So what we want to do is code the transforms in a function called transforms. We provide it a batch, and we transform the batch and return the transform batch. And so unlike doing manually everything in the collate function, we could do it using a transform. So we create a transform function on a batch. So you provide a batch input to transforms, and all you need to do is return the whatever transforms you do to the batch, return the batch transformed. Okay, so what goes in is the batch, what comes out is the transformed batch. But the requirement of Hugging Face is you must return from the transform function a transformed batch. So that means this function must return a transformed batch. Okay. So that's what I comment here, that it expects the with transform function to return the new version of the data. So this return is necessary and expected by Hugging Face, right? Now, the interesting thing is PyTorch knows how to collate not just tuples, but also dictionaries, because PyTorch is built in as a framework. It wants to support all of these. So Hugging Face data sets, whether it's a tuple or whether it's a dictionary, PyTorch is able to support it. So we have a dictionary of tensors using the transform function, right? So we don't need to build a custom collate function where we're converting a dictionary and returning a dictionary. Why? Because PyTorch is capable of handling dictionaries. And so without creating a custom collate function, transforms neatly provides us the ability to just return what we desire from the data set. And we can just create a data loader from the transform data set with a batch size, and then get back what we exactly would want as before. The important thing to realize is that the with transforms, that's this guy, runs on every element, and when every element is accessed, because when every element is accessed, it uses the dunder get item. And this dunder get item will call this function on the fly, so the transforms can have many data augmentations. So this transform within this current example is very simply just converting it to tensors, can in the future do a variety of augmentations, stretching, twisting, flipping, things like that that I mentioned. Okay, so this is just a simple example of a very basic setup of Hugging Face transforms and how to create a data set in a data loader and get back to what we wanted, what we had set up the training loop to be. Okay, now here's where Jeremy begins to introduce some of the capabilities which are not inherently necessary to understand the functionality, but he is beginning to introduce Python concepts and a few other bells and whistles, primarily so that the framework that he is building makes it easy to process a variety of models and helps us work with a variety of data in a very quick and fast iterating manner. Okay, so none of the steps that we are going to get into in the rest of this notebook are essential to understanding how Hugging Face data sets work and so on. It's just so that we are progressing in a direction which will enable us to kind of get stable diffusion in many of its components coded and understood and able to be manipulated very quickly. So the first step we take along kind of a direction is to say, well, this function is a function that returns the modified data. But what if we wanted transforms to not return something, but to modify the batch in place? So the simple thing he wants to do is he wants to change the transform function to not return the modified batch, but to modify the batch in place. Okay. But remember that Hugging Face, though, expects the transforms to actually return the transformed batch. Okay. So that is something that we still need to fulfill if we are going to use transforms in Hugging Face and to support the train with transforms and create the transform data set. Okay, so the desire is to transform B and to do it in place, just like he has illustrated with this made up function, calls it underscore transform I, and we'll kind of understand why. This function is given a batch, it just modifies the batch in place. Notice that there is no return in this. It just takes in a batch, modifies the batch in place. So how do we use this function but fulfill this requirement? So that's the question, the answer to which will expose us to the decorator concept in Python. So in order to do in-place transform here, here's what we do. We create a function called in-place, send in the function that we are having here, which is, you know, the f, send in a, or let's even forget what we're trying to do. Let's just say, what is this function in place doing? The in place function is taking a function f, which is given to it as input, then it calls the batch on a new function, which is the underscore f function. It calls the function f that we give to the in-place function, returns the batch, returns the result of f of b, and the in-place function then returns the new function underscore f that we've designed, right? So the in-place function is a function that takes in an input and returns a modified version of the input. Right. So it's a function that returns a function. So let's go through what the explanation here is. So take the function, in this case, underscore transform I, pass it to another function to create a new function, right? Which is a version of this in-place function that actually returns the result. Right. Why is that necessary? It's necessary because the Hugging Face requires the return of the modified b value. But what we want is actually a function that does the modification in place. Right. So again, I would encourage you to go through, and I'll provide a link of a very simple book authored by I think Matt Harrison, which kind of takes you to the basics of a decorator if you've not been exposed to it in Python. Bottom line, you modify your decorator function using another function, and that's what a decorator does in Python. So the in place, which is called a decorator, decorates the underscore transform I function, converting it to a transform I function. So let's run these. Right, this is an in place transformation. This is a decorator that we want to code, so it modifies the underscore transform I function and creates the transform I function. The transform I function will actually return, even though our function doesn't do that. It's an in-place transformation, but this function that comes out of in-place actually returns the modified batch. And basically, if we say at in-place and then code the function that does the in-place modification, this formulation is nothing but what's referred to as syntactic sugar for doing that, and we can get rid of this underscore, which is just a placeholder function. So if we define the in-place function this way and put in a decorator on top of it, such as an in-place, we get what we need. That is a function that does the in-place modification, but because of the decorator, the function that is returned from here is actually a function that returns the modified batch and satisfies the Hugging Face requirement. So that's what we are doing by using an in-place decorator to our in-place transform function. And if you want to understand the basics of decorators, go check out this book. It's fairly good and is very focused just on decorators. Okay, so now that we have done that, we do a transform data set, train the transform, and then we use transform I and get the transform data set 0. We print the X and the Y, and we figure out that we haven't changed anything. Now, we can further simplify the execution of what we have done here by using what is called an item getter, which is in Python, again, a function that returns a function. So let's say, for example, a D is a dictionary with these keys, and IG is an item getter of A and C. So what basically IG is it says IG is a function that will return the A and the C key values from this dictionary. So IG, when you pass it the input of dictionary D, then you get the key values for A and C. So it returns 1 and 3, right? So the important thing here, again, it's a slight detour to say Python is a dynamic language. So it doesn't matter that what you pass into an item getter. It doesn't exactly have to be defined as a dictionary. You can define a class and have a get item. This get item code is essentially doing the same thing as this. If it returns a 1, if the key is A, it returns a 2. If the key is B, otherwise it returns a 3. So you make an instance of the D class and you run the item getter and pass in the D. And D here, as you can see, is not a dictionary, just a class with a get item. And this is where Python's dynamism comes in, the fact that it's a dynamic language. So if it acts and quacks like a dict, then it's a dict. So basically, you get what you used to get from the item getter. Or what I was playing with here, basically when you list the tdsf.features, it still gives you image and the label. So when you do a batch and you pass in 2 dictionaries, right, then PyTorch default collate function is able to collate. Remember what we wanted to do with the collate function? We wanted to transpose and combine the keys appropriately, or combine the first elements appropriately and the second elements in the zip star B function that we looked at. You can see that this does exactly the same. Batch is a dictionary of 2 values, the A's and the B's and the A's and the B's. You see what the default collate does. It takes the A's keys and combines them, and it takes the B keys and combines them. So even a dictionary, when you pass it, same like the tuples that we saw passed in previously, it gives us the tuple, or it gives us actually, again, returns a dictionary. But in this case, the dictionary is transposed. All the A's are combined together and all the B's are combined together. Does that make sense? Is that clear?
Yeah.
Go back and compare, what happened with the zip star B, and you'll see it's the same thing. So therefore, a collate dict function, right, is you can create a collate dict function and pass it a data set. This data set has dictionaries, not tuples, and you say get item getter, and of the features of the data set. The reason you do that is the features are the image and the label, and those are the values that you want to collate together. So you want the collation of all the images in one and all the labels in the other. So that's why you say get is an item getter. So this is a function to which if you pass the dict, or what looks like a dict, then it will give you back the collated corresponding stack of the appropriate things put together. So now we return a function that simply calls item getter on default collate. So that means you return a get, and the get is an item getter on the default collate. That means it will return these values. And this function, so collate date ds returns a function. That function actually will give us what we require, right, which is the appropriate tuples, right? And so that's what we do with the Hugging Face data loader. We create a data loader transform. So it creates a data loader. You provided the transform data set, batch size of 4. The collate function is the collate dict function that we provide. And to that, we provide the transform data set, right? The transform data set is just, whatever transform we need to run on it. And then we get, what we get out of it is 4 values of x's and the corresponding 4 labels, right? So what it does, you can see, so collate take and used to convert and provide the tuple output from any data set, which is transformed, that works with dicts such as Hugging Face data sets, right? And then I just have explained what the NB dev creates the modules from the notebook and how that all works. Okay, I think in the interest of time, let's just stop here and we'll go through the remainder of this and begin to go through the callbacks and the setup for lecture 15 next week. And we'll try and get through probably the initial part of lecture 15 if we can get there, or take the time to just understand the plotting of the images and the callback functionality or the basics of Python as Jeremy lays the foundation for how he wants to subsequently manipulate the training loop so as to build what we call the learner and the framework for that, which will enable us again to very quickly work with our data to be able to manipulate things fast and quick so we can do a lot of experiments. So just to summarize, we've gone through data sets, data loaders, looked at how a collate function, looked at samplers, looked at what kind of variation is there in Hugging Face data sets, how to access them, how to have a collate deck, how to use a decorator in Python to kind of help create some of the functionality while being compliant with Hugging Face requirements. And that's the journey today. Okay, any questions or comments before we log off?
No, thank you.
Just wanted to say now I understand why I use collate dict. I used to do it blindly. So
yeah. That's the thing about these kind of stuff that it kind of periodically reminds you of the fundamentals. And retouching the fundamentals once in a while puts you, I think, on a stronger foundation. Okay, thanks everybody for joining. See you all next week.
Yeah, thank you.
all right, thank you.
Thank you.